All right, welcome back, everybody. It is 1:30 Eastern. We are going to go ahead and get started. This next session is a response to another reverse pitch. To start us off, we're going to have Kevin Thompson from Duke and Todd Leclerc here. All right, Kevin and Todd, over to you.
Thank you. Yeah, as we wanted to start out to talk through, then I'll also hand it over to Todd with C3, who will talk through some additional information on how they have helped us solve this challenge as well. So, just kind of again a refresher of Monday. What we have come up with is a transmission health and risk management platform, and this helps manage our assets. And the things that we are looking for this solution to deliver to us are down here below. So we're looking for a predictive system that will give us our asset health and risk-driven work schedules. We're looking for prescriptive, something that will give us suggestions in terms of what repair or if a replace decision is needed, but to provide us with those suggestions or preliminary thoughts along the way, with the goal of extending the life cycle of our assets. We obviously have older assets on our fleet, which I think is similar to all utilities, and they are aging out faster than we could replace them based off of a time-based replacement schedule. So we need a way to prioritize our assets based on their health, not based on their time, in order to be able to solve this issue. And also, we're looking to reduce asset failures or catastrophic failures. Catastrophic failures being, the worst possible, where they're destroying other pieces of equipment or taking down an entire station, or in the most severe instance, causing harm or injury to one of our employees. So the goal is to reduce the amount of failures and catastrophic failures and turn those more into maybe emergent replacement projects or just-in-time replacement projects or corrective actions that will prohibit or reduce these failures from happening. One of the other pieces we're looking to do with this solution as well is capture asset travel knowledge. As I'm sure with most utility industries as well, we have a very senior staff of field technicians, and at some point they will be retiring, and at some point that knowledge base will go away. We are now in a world where we do not maintain everything all the time, and so we lose some of that tribal knowledge and just hands-on experience with that equipment. And also, if you've been dealing with that equipment for 30 years, you know certain things about that equipment that other folks just coming onto the job might not know. So, one of the other goals of this solution is to capture that tribal knowledge in a database. The goals for this whole thing is to improve our system reliability and integrity, and also to manage the budgets with asset growth. And so I mentioned on Monday we have challenges with O&M as well as capital spend, and we really have got to make every dollar count now in today's environment. And so this solution is going to help us get there. This next slide here is just kind of the architecture that we have worked with C3 in solving this problem for us. It's quite a busy slide, but I'll try to walk through it from left to right. If you look on the left-hand side, those are the assets and equipment that we're focused on. So we're focused on transformers, breakers, and then also the condition-based monitoring monitors that we have out there on the system for those associated pieces of equipment. If you see the green arrows and the orange arrows with the bubbles kind of floating over, those are all just our different data sources that we have for information around transformers and breakers and CBM equipment. And then we're bringing that all over into a data hub and also to the Pi Historian for the monitors. You see the little Pac-Man ghost there. That's our little fancy firewall. But then it all goes into our C3 HRM application, where we take the machine learning analytics and modeling and we produce a solution. It houses both our engineering analytics as well as our machine learning analytics. Also, one of the other things I'll mention, kind of in the middle of the screen, one of our sources in the data hub are outages, and so that's one of the critical pieces as well. That helps the machine learn and tell us what active transformers we have that may be performing along the same trends as some of the assets that we have seen failed. And so we bring that data over into the HRM application, and then some of that machine learning and analytics model information goes right back into the data hub to help continue to make it learn. And then to the far right of the screen, here are the different outputs that we look for the solution to provide us with, and benefits as well. So, what this solution provides us is a health and risk indice. It provides us health scores for the particular asset that we're talking about. It also provides us with criticality or risk scores, which tell us, it distinguishes the transformer or the asset to the type of station that it's at. So maybe it's a critical station which doesn't have appropriate backup if it went down. And so that gives us the risk part of the health and risk scores. One of the other benefits of the solution is asset prioritization. This allows us to prioritize our capital replacements and come up with a budget for the upcoming year of what needs to be replaced and when. It provides us with an asset watch list, so we can see when the scores degrade enough. We will get alerts about those degradations, and then our experts will have the ability to put that asset onto a watch list. And so that provides us the ability to maybe pull oil samples more frequently, run some different tests on it if we're seeing some signs of questionable activity there. It also creates for us automatic notifications. We haven't gotten into this realm yet, but it will email notifications to our technicians if alerts go to needing to make them aware of them. Right now, we have the alerts notified just within the system, but we will evolve to having them emailed or text to the individual that needs to see that alert and address it. We're also looking for it to provide us asset sparing support. I mentioned that on Monday. That's one of our critical pieces of information on how we spend our money as well. It will provide us with where do we need to have our spares and how many spares do we need to have according to the health score and when we can possibly get that replaced. And then just some predictive analytics information and failure tracking and trending. I mentioned the failure tracking piece of this will tell us, where it will help learn the machine as to look to our current transformers or current assets and let you know if it is following the same trend of any active assets. And then down here at the bottom also is a very key component that we built into the process as well, is our subject matter experts. As I mentioned before, we've got folks out in the field and experts with 30, 40 years worth of knowledge. Right now, and we spoke to this over the last couple of days, because we do not have the volume of data and the quality of data to solely rely on machine learning, we must leverage our subject matter experts to look at and evaluate the data and tell us what it's saying. Just because the system gives us a score that says this is unhealthy and needs action taken doesn't necessarily mean that we need to immediately go and react to that right now. We are still heavily requiring our subject matter experts to look at the information and interpret it and tell us where those analytics might be incorrect or something like that and needing adjusting. And that's how the system will learn, and that's how we will ensure that we're doing the right things to maintain our fleet. Here's just a slide here that kind of shows some of our criticality and health components that we have out here. We don't have all of these indices feeding in, but this is just a good idea of the items that you could bring into a health score and a criticality score. So for the health score, you see we've got nameplate information, the condition, monitoring and sensor data, inspection and maintenance records, work order history, voltage measurements, load profiles, and then down in the criticality section, we might have things, faults or outages, oil spills, how much oil is in the transformer itself, how close to navigable water is it. Those kind of different things can be in your criticality score. And then those together give us our total risk score. So from here, I'll turn it over to Todd to give you an overview of the C3 AI solution.
All right. Thank you, Kevin. Appreciate that fantastic overview there. I mean, obviously the team at Duke has done a ton of work in developing the HRM application. It definitely shows. Just to quickly introduce myself, my name is Todd LeClaire, and I'm a senior director in the utility segment here at C3 AI. We've been working with Duke, Kevin, and his team to assist them in their journey to leverage AI and machine learning to more efficiently and proactively maintain their equipment. So as part of the EPRI reverse pitch event, we wanted to really showcase what our customers are doing with the C3 technology, and then pull back the curtain a little bit and spend a few minutes talking about the solution and technology that's supporting these use cases. So when looking at the overall event and the reverse pitch in total, we were asked to put this slide together, and just want to quickly touch here. This presentation, as you can see, is mostly focused on asset management, but I just wanted to quickly communicate that the C3AI platform and applications have been and can be utilized for a variety of use cases, from grid analytics to customer-facing, customer segmentation and targeting, to assisting in decarbonization efforts, et cetera. It's really a tool set to tackle a wide variety of problems. So just quickly, who is C3? If you missed the keynote session, one of the keynote sessions earlier this morning, C3 is a software company that provides really a suite of solutions that enable organizations to design, develop, deploy, and operate AI and advanced analytics at enterprise scale. While we have services capabilities as an organization, our focus is really on leveraging our software technology to empower utilities to extract real business value. To accomplish this, we provide a couple of solutions, with our primary offering being the C3 AI Suite. The C3 AI Suite is an end-to-end AI and machine learning enabled application development platform. Within it are features that accelerate the time to value for addressing any given use case. And it all starts with data integration, where we have many pre-built connectors to common utility systems like Maximo, SAP, Oracle, MDM system, CRM system, OMS, DMS, ADMS, et cetera, including the ability to work with a variety of data types like structured, unstructured, image, video, and either streaming or batch formats. That data, we then place it into an extensible data model, either by industry or by application, and we're able to persist or virtualize that data across a variety of stores and infrastructures. The suite itself contains a set of security, governance, data lineage, cataloging, as well as AI ML model development and application development tools. Now, in the blue box you see surrounding the C3 AI suite, that's really fundamental to our core value proposition, is that we built everything on a model-driven architecture. The model provides an abstraction layer that defines all components, data, and services in metadata, which reduces complexity in both developing and maintaining data-driven applications. In addition, our platform is open and extensible. It's really the opposite of a black box environment. It has the ability to work with both best of breed and existing technology investments. Included in that openness is always full explainability. We believe transparency is paramount to accelerating AI adoption. And what I mean by explainability is an evidence package that supports a prediction made leveraging C3 AI software, so an operator might be able to go in and see what is contributing to that specific asset risk score. So our underlying technology really powers some of our complementary solutions, and that includes our C3I applications, which are, think of those as SaaS applications to address high-value use cases, predictive maintenance, sensor health, revenue protection, and then Ex Machina, which is our low-code, no-code citizen data scientist tool with auto ML capabilities. So when looking at the utility value chain as a whole, there's a wide range of use cases that can be addressed, from generation to transmission to the customer. And really with the changing electrical landscape, the sectors are becoming more interconnected and interdependent than ever before. Utility organizations historically and still today are siloed within their respective operational areas. Within those areas are valuable systems and data stores that can have an impact up and down the value chain. Today, you heard about Kevin's work at Duke focused on addressing predictive maintenance specifically for the transmission network. And again, here's a diagram of the system architecture Duke is using to power their HRM application. On the left, you have the data sources coming in via Duke's data warehouse, from Maximo, GIS, Doble, inspection reports, as well as data streaming in directly into the C3 AI model-driven architecture. Then within that architecture, that's where the AI ML analytics are being created to then generate dynamic asset scores that are being operationalized in intuitive user interfaces. So what quick comment about what's unique and compelling actually about this particular deployment, as Kevin mentioned, is the use of people and the use of more of those traditional physics-based engineering analytics as input features to the AI ML models. Because our approach is fully open, Duke's engineers have been involved since day one in the design, decisions, training, and validation of the dynamic asset risk scores, which really has improved the level of confidence in the results that they're seeing from the system. And last but not least, those results. Overall, this has been a great experience, and it's really a solid example of how we're applying operationalized AI ML at scale to address utility organizations. So appreciate the time today. Kevin, thank you for joining me here today, this afternoon, to help talk about how we're using technology to address utility use cases. Hannah, I will turn it back to you.
Thank you so much, Todd and Kevin. That was awesome. All right, so we are going to go next to Gregory from Westinghouse. Greg, you have the floor. Over to you.
Thanks for dialing in, everybody. I think my screen here is coming up here. Give me a minute. Yeah, there it is. Okay, so I'm presenting on behalf of a team of us who work in the area of vibration analysis and specifically reactor internals monitoring for nuclear power plants. So what I'm presenting here is a narrative of a specific instantiation of us doing machine learning, artificial intelligence-based work for accomplishing tasks related to structural health monitoring that then feeds into condition-based maintenance and inspections of critical reactor structures. I'll first describe what I'm talking about when I say neutron noise. Then I'll discuss some precedent that we have for use of neutron noise in our pressurized water reactors across the states. Then of interest to EPRI, a conference like this, I presume will be some of the more recent activities we've been doing in the area of research and development. And then finally, I want to discuss how what we've done here, although it's nuclear specific, is generally extensible to all sorts of applications relating to dynamic analysis and assessment of structural health. So why might one monitor a set of reactor internals using neutron noise analysis? We can detect abnormal vibration from degraded components. The nuclear fleet nowadays is aging, and as such, things are happening to the structures, and we need to proactively mitigate those as best as possible. I have some examples listed here. Thermal shield supports are breaking, hold down springs are relaxing, sometimes loose parts become wedged in the reactor, and the fuel assemblies sometimes vibrate excessively due to things such as baffle jetting attributed to baffle former bolt damage. So we can use neutron noise to detect the onset of these phenomena, track the progress, and sometimes even disprove the existence of them in the first place. So all pressurized water reactors in the world come with a set of X-core neutron fluence detectors, whether they're designed by Westinghouse, Combustion Engineering, or somebody else. And so those sensors are illustrated by the blue dots that I'm showing about the perimeter here of the reactor pressure vessel, and along the elevation here, where you can see that they're at an elevation consistent with the nuclear core itself. Whenever we acquire the signal from those neutron fluence detectors, it looks like this conceptual sketch here, where there's a steady state component that's proportional to the reactor power. And so that's insightful from the standpoint of understanding what's happening in the space of the nuclear reaction / power generation side of things. But what I'm interested from the standpoint of what I call the mechanical engineering or the vibration analytics is this dithering portion about that mean. That's the AC or alternating current portion of the neutron fluence signal that we refer to as the noise. That noise is generated by this illustration here, where again the DC level is proportional to the neutron flux, and the AC level is what we call the neutron noise. So variation in the water thickness that exists between the internal boundary of the reactor pressure vessel and the reactor internals, that variation causes attenuation of the neutron flux and therefore contributes to the change or variation in that as measured signal. So again, although this is a nuclear specific example, just think of this as an accelerometer measuring dynamics of anything that's active in a nuclear plant or wherever, on a bridge subject to traffic loading, or a wind turbine subject to wind loading. Same exact idea here. The sources that we need to account for in this specific situation of neutron noise include the following. There's thermal mixing, vibration attributed to the fuel assemblies, the core barrel, thermal shield, and reactor vessel itself, as well as acoustic phenomena that imparts to the dynamics of the reactor structures, such as initiated by reactor coolant pump pulsations. Other sources that we need to account for include those listed here. Again, in our specific instance, we need to account for a correction on the as measured data associated with the water temperature, as well as the boration level of the water. But these are the sorts of corrections that need to be made across any given vibration analysis application. So whenever we're practically doing a vibration analysis of some structure from which we have measurements, we need to include those factors that could introduce some non-negligible bias to our as measured signal, and then appropriately remove that bias in order to make an assessment as to what the true signal looks like. Here's just some illustrations of what these vibration modes look like spatially. So there's the beam mode, just a cantilever beam mode of what we call the core barrel that kind of goes back and forth inside of the reactor pressure vessel. From kind of a top-down perspective, the thermal shield, which is a cylindrical annulus structure that surrounds the core barrel, can exhibit flexural modes, such as are shown here as an n=3 shell mode. When it comes to how we go about doing our neutron noise analysis, we largely make use of information available from dynamic finite element simulations. And so on this slide here, I'm just pointing out that we've benchmarked our finite element analyses using hydrodynamic coupling to a lot of measured data that we've accumulated over the years. So now, from the standpoint of understanding degradation that could exist in the reactor structures, here's some cartoon-style diagrams that illustrate how the vibration signature might change. So we take that as recorded signal in the time domain that I showed on the prior slide, that AC or that noise component. We can take that, that signal that's in the time domain, transform it into the frequency domain, such as using a power spectral density analysis. And we can look at what we expect to see in that power spectral density function plot and compare that with what we now see in some newly acquired set of data. And so on this slide here, it's just showing 3 different scenarios of how damage can manifest itself as changes on a power spectral density function. So that ultimately reveals symptoms of possible degraded conditions that's useful for us when it comes to diagnosis. Some recent experience that we had with a power plant in the United States. In spring 2019, during a refueling outage, a plant experienced difficulty removing the reactor vessel upper internals because there is significant degradation at the thermal shield support blocks, thermal shield flexures, and baffle former bolts. So that proved problematic. It extended their outage. It was a challenge. It introduced financial concerns to an operating nuclear power plant. So in order to address that, we pulled up our dynamic finite element analyses, as well as some neutron noise data, to diagnose the state of the degraded condition. We used the finite element analysis in conjunction with neutron noise monitoring to evaluate multiple degradation scenarios that could conceivably have caused this to happen, and therefore predicted that there were indeed multiple non-functional structural members that we call flexures that existed in the plant. So that then allowed us in the outage season of last fall to go in and, with our eyes wide open, replace the components that we found to be damaged using the combination of our simulation technology and our analysis of the neutron noise data. So just an example here of what we could consider to be prognostic health management or condition-based maintenance, in the sense that we were able to monitor a condition of the reactor structures and then inform the maintenance that occurred in the subsequent outage season to replace those things that needed to be replaced. In terms of what we're up to most recently in our research and development department, which is where I work within the company, is we've looked at 3 different types of tasks related to enhancing neutron noise analysis with machine learning methods. So those 3 work streams are what I have listed: data analysis, mechanics-based analysis, and monitoring, where this slide here highlights the first 2. So upon acquisition of the data, we then feed that as acquired data in the time domain into a computational tool by which we can perform data analysis. That data analysis could be thought of a means of feature extraction. So we take this otherwise messy signal. It contains a lot of information. We transform it into the frequency domain, and then we do some, I guess, what I'd characterize as advanced signal processing to then extract those features that are most meaningful to explain the health of the structures. In conjunction with the data analysis, we can pull up our finite element simulations, and we can look across the parameter space that could conceivably explain degradation that may or may not exist at a given plant at any given point in time. And we can develop from our finite element simulations the sensitivities. We can understand that, okay, if you have these bolts there broken and that spring there relaxed, we'd expect the direction of change of your beam mode to be here, or the direction of change of the amplitude of your shell mode to be there. And that's the sort of insight that we infer from executing our finite element simulations through a set of computational experiments. So we take the insight gained from our finite element simulations, as well as the features extracted from our data analysis, and toss that into a monitoring platform. The monitoring platform that we have, I'll discuss here on the next slide. So from the standpoint of monitoring, we can break that down into 2, maybe 3 tasks. The first thing we need to do is detect whether or not the behavior is anomalous in the first place. So we need to first aggregate the data. So on this table here, it's intentionally not that legible, but just think of each row of this Excel spreadsheet snippet as being a given point in time at which we acquired data. In our case, again, it's neutron noise data, could be any vibration data set, something pertaining to the dynamics. And each column of this spreadsheet represents a feature. That could be the frequency at which some vibration mode is occurring. It could be the amplitude. It could be whether or not there's impacting and such. We then take that aggregated data, toss it into a pattern recognition analysis algorithm, regression-based machine learning. And then by using the regression-based machine learning, we can then assess if there are differences between the observed and predicted. We can perceive if there is anomalous behavior. And using the software that we're working with, we can produce an anomaly detection report that's useful to those who are at the plants using such a tool. So I think the anomaly detection piece is interesting, but where I feel we've really offered some significant value is from the standpoint of diagnostics. So we can use machine learning, we can write up MATLAB, Python, use commercial softwares, whatever, to do the anomaly detection piece of things. But really where the rubber meets the road is, can you actually diagnose what's happening upon detection of that anomalous condition? And if you can diagnose it, then you actually have some hope of credibly prognosticating the remaining useful life. Otherwise, we're just hoping. So from the standpoint of diagnoses, we can take the sensitivities deduced from our benchmarked finite element simulations and nest those sensitivities in what we call a conditional probability table that resides within a Bayesian belief network. And in so doing, in a probabilistic sense, make an informed assessment as to the probability that some degradation form may exist based on the interrelationship amongst all the different features that we're extracting from the as measured data. This is just a picture of our monitoring and diagnostic platform. As Westinghouse nowadays, I believe we're calling this asset life predictive maintenance. And again, this is just our cartoon style illustration that I think just lists cities instead of actual power plant names, but you get the idea that we can provide a report that has to do with the existence of a potentially anomalous condition, and then a diagnostic description that's informed by our underlying analytics. I'd argue that what we're doing here in the space of reactor internals monitoring is akin to what in the literature nowadays people are calling digital twins. So digital twins can be defined in a number of different ways, but this diagram here is a way that we've found helpful to think of it as of recent, where in the orange rectangle we have a physical component, in the blue rectangle we have a digital representation of that physical component, and we have ways of the data being able to interact between the physical component and the digital representation so that we can ultimately provide meaningful analysis to the stakeholder. So in summary, I'm offering one definition here of a digital twin that's courtesy of Dr. Malha's group down at Vanderbilt, where he states it's a virtual representation of a physical system and its associated environment and processes that's updated through the exchange of information between the physical and virtual systems. And I'd say that's exactly what we've done and what we're now doing in the space of neutron noise monitoring for reactor internals and the associated enhancements that we're now introducing via machine learning-based methods. So that's the extent of my presentation, and thanks for listening in, and also thanks to the other presenters for sharing your work. It's interesting to hear.
Great job, Greg. Thank you so much. All right, guys, we are going to transfer over to Michael Segala from SFL Scientific. Michael, I am going to pass the floor over to you now. Good luck. Thank you very much.
Great, thank you. And just mic check, everybody can hear me okay? Sounds good. So perfect, everybody. I'm going to give a very quick background on myself, just to set some perspective. So my name is Mike Segala. I'm the CEO and co-founder of SFL Scientific. I did a PhD in particle physics about a decade ago or so, right when the data science space was really starting to take form. So when I started the company, my co-founders and myself, right, we're really focused, and we'll talk about this in a second, about how do we build systems that are kind of hard from a data perspective, hard from a compute and infrastructure perspective, and then obviously very challenging from a novel algorithmic perspective, right? And if you kind of couple these things together, this is really what modern day AI has transformed into. So, is this thing working? Yeah. So just from an SFL perspective, we're a US-based data science consulting company, and our kind of mandate is to develop and implement AI solutions for our customers. We've had the opportunity to work with EPRI on several kind of large AI projects, which I'm going to highlight here in a few minutes. But the goal of this talk, just to be very clear, is not to showcase you some cool use cases or cool AI and talk about how easy it is and, you know, all these fun and flashy things. It's actually quite the opposite. AI is actually an extremely hard field, and it's very hard to productionize and really get value out of. What I want to really talk through very, very quickly, because we don't have much time, is what are the aspects that people struggle with? Where do we really lack true adoption, and how can we overcome some of these barriers such that, especially in the industry of, you know, power and utility space, we actually can start incorporating some of these things in a real world, right? Not just in a standalone POC, but actually how do we get real ROI and productionize against that? And this larger picture is what we really need to do to adopt these real practices. So very kind of silly basics to start here, but this really sums up the true state of AI, right? Like everybody's talking about it. Nobody knows how to do it. If you look from an executive perspective, at least 85%, and I think this number is actually woefully misrepresented in small, it's probably much higher, say that they all need AI because of something, some market pressure, some automation, some innovation, right? They know they need it, but they all really struggle to adopt it and to get any real ROI out of it. So the question that we want to answer here in an extremely short amount of time is, well, why is that? And how do we start thinking methodically about overcoming some of those challenges? And we're going to advance through some of this and make it a little bit more technical as we go. But, you know, in any organization, whatever you're building, there's always a very high barrier of entry when you're building a new technology unit. And that's either when you're buying a solution from a vendor, and it might be a very great vendor like a C3 or somebody else who has a very great core product, or on the other side of the spectrum, like my company who builds something novel. It's always still an extremely hard kind of lift to say, I want to incorporate a completely net new technology stack to my organization. So from a leadership perspective, right, you really need to invest in what are my operational outcomes going to be and how am I going to adopt this? AI is an extremely different than traditional kind of plug and play software because there's this clear interplay between, you know, we need to think about data collection, we need to think about anonymizing and analyzing that data, all the way to kind of probabilistic code in regulated environments, right? There's no longer these kind of if-then statements, which are highly tangible and deterministic. We're actually completely away from that system. So getting to that point is actually a really hard mind share, right? It's a mind shift. So we're going to have to think about that and how to overcome some of these challenges. So for us, right, a common theme that we think about is installing kind of best practices across the space and really leveraging experts that have a very rigorous kind of agnostic technical process to think about how do I actually solve specific situations for my actual line of business, for my actual use case. The problem is, right, when folks talk about data science or AI or ML or DL, right, we talk about words all the time, right? People tend to think very hard about the algorithms. What's the latest and greatest? What's the state of the art? What's the coolest, biggest BERT model or computer vision model out there in the world? Because that's fun, right? That's the cool stuff. However, to actually implement AI, it's so much more than just algorithms, right? You really need to think about this holistic strategy and implementation plan to be successful. So for us, right, in our space, we're working with clients really across this entire development pipeline from strategy, where we're saying, okay, let's sit down and actually define the appropriate starting place for AI for our business. Not for the IBM commercials out there or anything else like that, but for us, what are we really trying to achieve? What are the use cases? What's the ROI? What are my success metrics going to be? Not just in terms of accuracy, but inferencing and SLAs and latencies and security, all the way down to resourcing and data availabilities and standards, right? So after that, then we want to have a very serious conversation about, well, what's the data engineering pipeline going to be to support that? How are we going to collect? How are we going to store, anonymize, govern this data? Again, not just in a POC, but when we're really deployed in the field and we have data coming to us, how do we make sure that that representation is the same and we're actually engaged in a way where we're collecting and storing that data appropriately? Finally, kind of from there, and by no means is this always sequential, but you can kind of think of it sequentially, right? Once you figured out those two components, then you can say, okay, now I'm ready to build something interesting. Now let's do some AI. Now let's build a POC where we can solve a problem in the matter of a few weeks and prove it out from a technical standpoint, and then move that into a more scalable operational environment, right? And again, that fourth bucket is also an extremely hard component. We'll talk about it in a second. But if you really want to be successful, not just in very kind of, silly AI that's really just in a POC and you're going to show some stuff, but it's going to fail, but to really go across this maturity curve, you're going to really have to think about this entire life cycle to be successful. And I'll add just one more kind of quick thing, and it looks like this table didn't render so well, which I should have picked up before. My apologies. Is, the way that we think about AI is not necessarily by industry. It's actually by the modality of data type that we're looking after. So these rows here, and again, you could probably download my slides. They're going to be a lot nicer rendered than this is. These are really the main buckets of problems you can solve in AI, right? They all kind of come down to very core fundamental data types, right? We have time series, signal processing type of data. We have natural language processing, and we have machine vision, computer vision images, things like that. And then we have kind of traditional analytics projects. To really understand how AI projects work, you need to really have a firm grasp on, what algorithmic methods and implications of these methods that you're going to use to develop. And again, not just in your certain field, because so much of the work that we do, from aerospace to medical to, healthcare and industrials, they all map across these same fundamental problem spaces and domains. You just need to be really thoughtful about, how do I deal with different modalities of data and solve problems appropriately there. All right, so one more quick slide, then I'll show you kind of use cases and bring some of this home. So let's assume that we're living in a space where we've defined a use case. And for the use case that I'm going to use is, let's assume that we have drones, and these drones are going to perform some visual inspection on cracks within a concrete structure. This is actually the use case I'm going to show you guys next. So the challenge in that problem statement is not really about what AI algorithms to apply. That's actually very straightforward. Again, there's really only a few things you can do, and you can do them pretty well. It really comes down to, what are the core 4 statements that you see in front of you? That's going to be your biggest barrier to really entry and technical objectives here. So the first 2, and you don't have to read these, I'll kind of just summarize in a second here, but the first 2 are really about data acquisition and validation in a generalized sense. And I want you guys to really hone in on this word generalization. So almost every project that we've worked on, which is probably in the hundreds at this point, if a customer comes to me and says, we've collected some data, let's do a POC. Let's imagine it's our drone, imaging problem. It's almost a certainty that what they have collected is not a very good representation of how that data will look in production, and or be robust enough to capture the real world environment that it's going to sit in. So for example, thinking about our drones, right? Let's just assume that our images in a POC were all taken in perfect daylight from 10 feet away from a crack, and we have this beautiful picture of all these cracks. I can train an algorithm in no time to find that with an extreme high level of accuracy. Great, my POC is solved. But now let's assume that we go and deploy this thing in the field, and for some reason we're only allowed to fly at night. And not only are we only allowed to fly at night, we only have to stay within 100 feet of the structure. So the entire optical range and dynamics of the problem has changed. You've completely changed the problem space. So what's going to happen? Our algorithm will fail. Our customers are going to be mad. Everything's going to come down to the fact that we didn't build the correct data representation to generalize the essence of the problem. And this plagues almost all of AI projects that we see these days. So if you take one thing away from this talk, it should really be, it is very easy to trick yourself into thinking your data represents the real world. As a rule of thumb, assume it doesn't, and always look to be improving upon that. The other biggest challenge that we see, I'm just going to call kind of change adoption. So many of the projects that we have, right, they'll show great technical success. We can find this crack, no problem, with great accuracies on all these things. But the problem is the people who are going to use it, it challenges the status quo of their day-to-day jobs. So think about the radiologist who now uses an AI algorithm to help diagnose cancer or a disease, or the NDT engineer who uses AI to find faults from the vibrational analysis or things like that. You are basically breaking their workflow and injecting a ton of risk that they own into their process. So they are naturally going to push back very strongly, because why do I have to adopt this? I'm now taking the risk. You guys are just doing cool technology stuff, right? That's where a lot of this stuff breaks down. So as leaders, right, on the technical side, on the business side, whomever you are listening to this, you must really educate and work with the actual experts who are going to use these systems to ensure that they're going to adopt it, they're going to understand it, and they're going to actually utilize your tech. Otherwise, you've done nothing, right? All the technical accuracy and greatness in the world means nothing if nobody's going to use it. All right. Wow, I'm going way over. I'm going to speed up here for a second. So here's an actual use case I just described. So, here we have drone pilots that fly around concrete structures, and we're tasked to develop a system to localize and detect cracks within these structures. So this is a project we've been fortunate enough to work with EPRI on, right? From a POC standpoint, the project was very successful in proving, right? Fundamentally, you can develop a set of algorithms that find defects at a very high level of accuracy. So if you look at the top row here, what you'll see is an example image on the left-hand side of the actual, right, real image, right? So, and basically in this middle column, and red is the cracks that the algorithm finds. And on the far right is green of what the humans actually annotated. So the first big thing that you'll notice is we basically are able to find all the cracks. Great, right? So we have really high levels of accuracies. However, what it also is finding is there's net new cracks, right? It's things that hadn't previously been seen before, right? So that's pretty profound. So not only are you finding everything, but you're finding net new things. Well, what are these net new things? That's a big question. In the second example on the bottom row, you'll see the same thing, but in this time on the far right hand, you're going to see this blue line. Well, it's something our algorithm didn't catch. Well, why? Is it the algorithm's bad? Is it the person who labeled the data incorrectly labeled it? I don't know. We have to figure that out, right? So what we need to do now, after you've proven out this first baseline, hey, this thing kind of works, is start to really understand the differences of, well, what's your model doing? What's the data doing? How are you labeling it, right? And this is really where the scientific process of AI comes into place, where you can't just run it once, set it and forget it and think you're okay. You really need to start digging in and analyzing and understanding the space. So what I just showed you is, again, right, baseline performance. This is often, again, the easiest part of any project, just to prove out what you've done. So now let's assume you say, okay, let's create a system that actually isn't going to just work kind of standalone behind the scenes with offline images, but we want to work in a real-time environment and actually sit and do inference on the edge device itself. Significantly bigger, significantly harder challenge than just proving it out from a POC environment. So state-of-the-art AI systems are built with services, and this is just a mash pot of all sorts of different services here, but things like Amazon or Azure or NVIDIA from a GPU perspective or C3 from a platform perspective, there's tons of different options here. But the idea is really to start kind of merging the standard DevOps principles from users so they can actually seamlessly begin to integrate with some kind of containerized models or whatever it happens to be, such that you're auto-scaling during training and inferencing, and you're actually building in kind of these real-world scenarios to inference against. So these orchestration tools that you're seeing here, which we're very quickly talking through, right, begin to connect to different data sources, multiple environments, merge infrastructures, provide a more kind of easily seamless process so that you actually can move out of POC into production. But this is an extremely complicated process, and it needs to be very thoughtfully understood and implemented in an agile way, such that you're, again, not getting stuck at this integration effort between POC and prod, right? Because this is where we see so many of these projects kind of fall short. So winding down this use case, I just want to highlight an internal product that we've been working on, basically to enable, real-time embedded AI onto drones to perform a wide range of functions, right? Including visual inspection to a host of other kind of multimodal, anomaly detection, spectral analysis, ISR, all sorts of things. And I'm not giving you a product pitch by any sense here, but rather to say, the idea of adding AI to many kind of traditional and highly time-sensitive tasks like visual inspection, like NDT, and all whole sorts of other opportunities is now becoming extremely realistic, right? It is still a very challenging task to build a system like this, but with the correct technology, the correct data, the correct adoption mindset, you can easily begin your journey with tools and infrastructures and partners and ecosystems and actually start innovating, right? And not get stuck in this endless cycle of kind of failed pilots. So I had another cool use case. I'm going to probably skip over it, but same kind of philosophy here. Here I was going to talk about the need of synthetic data and injecting all sorts of synthetic data for scenarios where you don't have a real enough environmental information. But I think you guys get the point here of saying, like, it's not good enough to just set and forget kind of AI systems. There's all sorts of different ways to make these things a little bit more robust and correct. But we obviously do quite a bit of work in the NDT space as well. All right, so last slide here, while I want to kind of only have about a minute or two left here, is just highlight, and then I'll be finished it. A few things to talk about from a workflow of a successful AI pilot. And I know I've covered a significant amount of random information, but I hope this is making sense in some way. So, we suggest, if you're a data science team, if you're a data scientist, if you're working in the space, if you're thinking about the space, to determine real baseline feasibility, you should be aiming 4 to 8 weeks. Something in that time frame. You can solve almost every problem to say go, no go within a 4-week, 8-week time sprint. Longer efforts usually mean the problem isn't scoped appropriately, or it's way too complex from a baseline feasibility, or you're solving a different problem on data wrangling or something else. You're not actually solving a real AI feasibility project. So teams really should consider the requirements in each project standalone. And this goes well beyond accuracy, right? It is not okay to just say, hey, I'm 80% accurate, that looks cool. What you need to think about, well, what does my inferencing need to be? How lightweight does that need to be? What is the performance? Is this going to be in real time? Is it going to sit in a distributed cloud environment? Will I have internet? Will I have remote sensing? Is this on a drone? What are the implications, right? Everything else that says, what is the real feasibility of this thing? Again, not just in a small POC, but really what it will look like moving forward. And this is how you ensure success. And as much as kind of the architecture determines how to scale these systems, cloud, on-prem, whatever, end users, whomever you are, you need to be talking to folks from IT. You need to be talking to your data scientists if you're not one. You need to continually examine workflows, talk to the SMEs, and really involve everybody in the ecosystem, because everybody in an AI sense needs to be involved in these projects. All right, so like I said at the beginning, AI is actually really hard, right? It's not very challenging to prove out an algorithm works in a standalone environment. It's extremely hard to build an AI system that works in a deployable sense in a real-world environment. So it takes a scientific approach to iteratively experiment and find optimal solutions. We're an AI consulting company. We'd love to work with you on projects. This is just a very small window of the stuff we do. So if this is of interest or you have other things that you want to talk about, just get in touch. And perfect timing. Done. So thanks, everyone.
Great. Thank you guys so much. That was perfect timing, Michael. Okay, it looks like we do have time for a question. So I will let Kevin or Todd answer first, and then we'll just go around the room here. So for the question, how much time and money is saved by putting these various systems into place? Kevin and Todd, over to you first.
So I'll start with that. I think it really depends on what your goals are. With the system, it should provide you with the right cost to spend on the right items at the right time. It should prioritize your spend. And so some downstream impacts of that, it should improve your reliability. It should reduce your outages or your emergency callouts. It should reduce the amount of repair work that you do that may not pay off at the end of it. Some of our AI and some of our analytics show that if you're seeing increases in certain metrics a particular type of repair will pay off and will benefit and actually improve the health of that asset, whereas other corrective spend could not necessarily benefit the health of that piece of equipment. But prior to this, you might think that that kind of repair was needed. And so on the other hand of it, in terms of cost, the solution may point out to you where you need to do more maintenance than you've done before, or more corrective work than you've done before, just based off of the health of the fleet and what you're after there. So it's got it's a balancing act there between the two sides. But I think at the end of the day, it should save you on improve your reliability, should save you on call outs. You're doing more proactive approach than a reactive approach. And then in terms of time, it really should save the end users a tremendous amount of time. There's a platform which they can go to and do an analysis of their entire fleet, not just one asset at a time, through multiple various different sources to come up with a proper evaluation.
Great. Thank you so much, Kevin. Todd, anything to add to Kevin's points?
Yeah, sure thing. So just to piggyback a little bit off what Kevin was saying there, on how it saves, the operators, the end users, the ultimate consumers of the data and the analytics that are coming out of some of these platforms. So there's the time and the cost savings on the platform, the AI infrastructure development itself. I think Michael actually alluded to it in his presentation where he talked about, the ML modeling and building and prototyping is one thing, but actually taking that from experiment to operationalize at scale, getting value on it is something different. So how C3AI views it and how what we've seen demonstrated success by using something like a model-driven architecture is really a range from sometimes 10 to 100 times faster and more cost efficient to use a model-driven solution. And so that's a cost and effort standpoint, but then there's a time to develop standpoint, where building all that architecture, connecting all those spaghetti of IT connections via structured programming, can sometimes take years. If you consolidate that using a model, you can shrink that down into weeks and months instead. So that's just from the C3 perspective.
Awesome. Great. Okay. We're at time, but I want to pass it over and make sure that Greg and Michael have an opportunity to answer as well. So speed round to Michael real quick.
I mean, it's a hard question because it's, the question needs to be use case driven. So you have two types of problems. You have operational problems where you can quickly map an ROI. Hey, I have 5 NDT engineers and I can speed their time up to give them more high priority tasks, and that is X amount of dollars. Easy, top line stuff. A lot of the problems in AI are still in the R&D space. So how do you really put a value on hard R&D problems? Well, you need to be very thoughtful about breaking down those processes. So there's no way that I can say you're going to save X amount of dollars, because everyone is going to be completely business and use case specific, but you need to think about it. Do I have a clear operational problem where I can map time to money? Or do I have a real R&D problem where I'm going to take some kind of scientific thought exercises and try some stuff, and maybe that's going to help 50 things downstream, and if we can start adding that up, maybe it helps discover something a little bit better or put out a fire over here a little bit better, right? Those are very different types of project statements. So there's no, by any stretch of this world, a one-size-fits-all value statement for what AI brings. It just has to be thought through completely from your unique perspective, and it's really the only case to be unfortunate.
But thank you guys so much. I know we went a few minutes over, so we will shorten our break just by 2 minutes to make sure that we start back here on time at 3:30 Eastern. 3 p.m. Eastern for our very last session. 3 p.m. Eastern, we will see you back here for our very last session of the day. Thank you very much.